Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about particle in a box. So, what is the classical view regarding classical in a particle in a box? So, classical case, you can see here, Q is equal to infinitive, Q is equal to infinitive, Q is equal to 0, 0 to L, and this is the one-dimensional box. So a perfect one-dimensional box, the walls are infinitely high, infinitely thick, infinitely massive, and completely impenetrable. There is no air resistance in the box. In the box Q, the potential energy is 0, and outside the box, it is infinite. The box has length L. So this information is important to understand the particle in a box of classical case. So outside the box infinitive and inside the box potential energy 0, and this is the length. Now in this figure you will understand a ball is a perfect one-dimensional racquetball court. There is no air resistance and ball is perfect. When the ball strikes the ball at L, it bounces off and hit the ball at 0 and keep the bouncing back and forth because the court is perfect, the ball is perfect, and there is no air resistance. Once the ball starts bouncing, it keeps bouncing back and forth infinitely. This is the conditions. We are considering here this ball is coming here, going there. So this is the length L. So these two figures, I think, important to understand particle in a box. Now, the quantum case. What are the difference if we consider quantum racquetball? The court is still perfect, but now its length is 1 nanometer, means 10 to the minus 9 meter, rather than 12 meter. So, the particle now has the mass of an electrons 9.1 into 10 to the minus 31 kg, rather than 0.04 kg. And this is the quantum particle in a box problem. Try to understand what changing occurs. 1 nanometer and in place of 12 meter, mass of electrons in place of this kg. Now, absolutely a small particle in the nano size box is a quantum particle, and this must obey the uncertainty principle, and that is del x del p is equal to or greater than h by 4 pi. If potential energy is 0 and x is equal to L by 2, we know both x and p. The result would be del x del p is 0, the same as classical racquetball. So this is impossible for a quantum system. Therefore, we cannot be 0. The particle cannot be standing still a specific point. So if we cannot be 0, then it can never be 0. The uncertainty principle tells us that the lowest energy that a quantum racquetball can have cannot be 0. So our quantum racquetball can never stand still. So energies of quantum particle in a box. You can see here. This figure indicating a wave function. This is the wave function inside the box, that is discontinuous. The wave function is called psi, or here phi. The vertical axis is the amplitude of wave functions. The dashed line shows the wave functions is 0, this dashed line, which must be outside the box. Must be some outside the box here, you can see. The wave function has non-zero value at the wall Here non-zero value at the 1. This is the 1. And then must drop discontinuously, not smoothly, to 0 outside the box. This is assumptions. Energies of a particle box. So, wave function must be 0 at the 1. So, the 3 examples of wave functions. Here 1, 2, 3, n is equal to 1, n is equal to 2, n is equal to 3. Phi or psi inside the box that are continuous. They have been shifted upward for clarity of presentations. The vertical axis is the amplitude of the wave functions, and dashed line show where the wave function is 0, which must be outside the box. The wave functions which have 0 value at the wall are continuous across the wall. So here how it is going, here you can see and here you can see. Now it will be more clear to you. Nodes are the point where the wave functions crosses 0. So here 1 nodes, here 2 nodes, crosses 0. So here crossing 0, this is the 0. So the sequence square of the first 3 wave functions, psi square for a particle in a box, they have been shifted upward for clarity of presentations. The vertical axis is the amplitude of the wave functions squared. The dashed line shows where the wave function is 0. The square of the wave functions are always positive because they are represent probability, and probability never be 0. So wave function shown in figure D can be positive or negative. Here positive and negative, but here always positive. So now, what is the important part here? Energies are quantized. So you know the energy half mv square, p square is equal to mv square, E is equal to p square by 2m, E square h square 2m del square, and lambda is equal to 2l by n. And so energy is equal to n square h square 8 ml square. This is the length. So there is a discrete sets of energy level for a given mass m and given box length L. Here m, mass, and L length. As the quantum number n, this is 1k square, 2a square, n takes 1, values 1, 2, 3, it is energy. So energy will be like this: h square 8 ml square, 4s square 8 ml square, 9h square 8 ml square, etc. Now you can see the energy level. N is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5. Energy 1, 4, 9, 16, 25. So particle in a box energy level, the quantum number is n, E is the energy, which increases as the square of the quantum number. And the energy is plotted in unit of h square divided ml square, so that it is easy to see how the energy increases. The dashed line is 0 line. This is the dashed line. This is 0 energy. The lowest energy level does not have E is equal to 0. So in contrast to a classical particle, a particle in a box. This is the difference. Now here n is equal to 1, n is equal to 2, n is equal to 3, E1, E4, E is equal to 9, and so on like this. So particle in a box energy level, the quantum number is n, E is the energy plotted in the unit of h square 8 ml square. This is the formula. The arrows indicate, you can use here this formula, n is equal to 1, here 4, like this. The arrows indicate absorptions. This is the absorption of photons that takes place an electron from the lowest energy level. N is equal to 1, to higher energy level n is equal to 2, n is equal to 3. For a photon to be absorbed, its energy must match the difference in energy between two energy levels. So this E4 and E1, you can calculate this energy difference. E9 E1, you can easily calculate the energy difference. So why are cherries red and blueberries blue? For answer, the color of fruit. Let's put in the number. H is equal to this 6.6 into 10 power minus 34 joule per second. The electron mass me kg. For the length of the box, let's take L to be that of the medium size molecule, and L is equal to this distance. Then you can calculate energy, this joule, and this energy correspond to lambda is equal to this 706 nanometer deep red color. So if L is equal to this distance, lambda is equal to this green color, and if L is equal to 0.6 nanometer, lambda is equal to this the blue color. So this is the why cherry is red and blue berries are blue. So answer of this, it depends on the length. Now particle in a box, step 1, first define the potential energy. This is your job. Then solve the Schrodinger equation. Then define the wave function. Then determine the allowed energy and then interpret its meaning. So from here I will discuss this point in our next video. If you like such type of video, then subscribe my channel, and thanks for watching.